So we have physics, mechanics, practice final exam, advanced undergraduate level. So let's begin part one. Number one, a particle of mass m moves along the x-axis under f of x equals f naught e to the negative x over L. Part A determine the potential energy. Part B, obtain the velocity as a function of position if x of 0 equals 0 and v of 0 equals v naught. Part C, determine the turning point if one exists. And part D, describe the effect of energy. Okay, so this is a one-dimensional motion with variable force problem. So we'll go over the setups and the answers for these at a relatively quick pace. So f of x equals f naught e to the negative x over L. That equals the negative derivative of u with respect to x. So du dx equals negative f naught e to the negative x over L. U of x equals f naught L e to the negative x over L plus c. So choosing here potential energy at infinity equals 0. U of x equals f naught L e to the negative x over L. And our energy conservation is going to be 1/2 mv squared plus f naught L e to the negative x over L. And that's going to equal 1/2 mv naught squared plus f naught L. So v of x is going to equal plus or minus the square root of v naught squared plus 2f naught L over m times the quantity of 1 minus e to the negative x over L. And our turning point here is going to require that v equals 0. So v naught squared plus 2f naught L over m times the quantity 1 minus e to the negative x over L, that equals 0. So e to the negative x over L equals 1 plus m v naught squared over 2f naught L. And x of t equals negative L ln quantity 1 plus m v naught squared over 2f naught L. And we could say here, so a real turning point exists only if the motion reaches that x sub t. So that's number one. Now moving along now to number two. Number two, we have the following. We have a projectile is launched with speed v naught at angle theta. A constant horizontal wind accelerates it according to a sub x equals negative beta v sub x squared. And our vertical acceleration is it remains a sub y equals negative g. So 4 parts here. Determine v sub x of t for part A. For part B, determine x of t. Part C, determine the total flight time. And part D, we want to approximate the range, assuming that this beta v naught is much less than 1. So this is a projectile motion with quadratic wind problem. So our horizontal equation here is going to be dv sub x dt equals negative beta v sub x squared. And dv sub x over v sub x squared, that's going to equal negative beta dt. And negative 1 over v sub x equals negative beta t minus 1 over v naught cosine theta. And also from here, v sub x of t, that equals v naught cosine theta over 1 plus beta v naught cosine theta t. So from here, then we could say x of t is this integral from 0 to t, v sub x of t prime dt prime. So x of t is going to come out to 1 over beta ln of 1 plus beta v naught cosine theta t. So our vertical motion is ordinary projectile motion in this case. So our y of t is going to equal v naught sine theta t minus 1/2 gt squared. And our flight time here is going to be capital T equals 2 v naught sine theta divided by g. And our range here is going to be r equals 1 over beta ln of 1 plus beta v naught cosine theta capital T. So isolating here, r again, r equals 1 over beta ln of 1 plus, substituting 2 beta v naught squared sine theta cosine theta divided by g. So for b sub beta naught is much less than 1, ln of 1 plus epsilon, that's going to approximate the following. Epsilon minus epsilon squared over 2. So what we're going to get here, r is approximately v naught squared sine of 2 theta over g minus 2 beta v naught to the 4th sine squared theta cosine squared theta divided by g squared. So that's for number 2. And now moving on to number 3. For number 3 here, we have a particle moves according to r of t equals a times the quantity 1 plus cosine omega t, and theta of t equals omega t. So for this problem, there's 5 parts. Find the velocity vector, the acceleration vector, the tangential acceleration, the normal acceleration, and the curvature of the trajectory. Okay, so for this curvilinear motion problem, we're given r equals a times the quantity 1 plus cosine omega t. So theta equals omega t. And r dot equals negative a omega sine omega t. And theta dot is going to equal omega. So what we're going to have here is velocity in polar coordinates is going to be v equals r dot r hat plus r theta dot theta hat. So our velocity is going to equal v equals negative a omega sine omega t r hat plus a omega times the quantity 1 plus cosine omega t. That times r hat. I'm sorry, that times theta hat. And our acceleration vector now, a is going to equal the quantity r double dot minus r theta dot squared r hat plus r theta double dot plus 2r dot theta dot times theta hat. So r double dot is equal to negative a omega squared cosine omega t, and theta double dot equals 0. So a sub r equals negative a omega squared cosine omega t. Theta double dot equals 0. A sub r equals negative a omega squared cosine omega t minus a omega squared times the quantity 1 plus cosine omega t. And then a sub r can equal negative a omega squared times the quantity 1 plus 2 cosine omega t. A sub theta is equal to 2 times the quantity negative a omega sine omega t times omega. So our a here is going to equal, so our acceleration vector is going to equal a equals negative a omega squared times quantity 1 plus 2 cosine omega t r hat minus 2a omega squared sine omega t theta hat. Calculating our speed here, speed is going to be v squared is equal to r dot squared plus r squared omega squared. So v squared equals a squared omega squared sine squared omega t plus a squared omega squared times the quantity 1 plus cosine omega t squared. So v squared is going to equal 2a squared omega squared times the quantity 1 plus cosine omega t. So our v equals a times omega times the square root of 2 times quantity 1 plus cosine omega t. Our tangential acceleration now, that's going to be a sub t equals dv dt, and that's going to equal negative omega squared sine omega t divided by the square root of 2 times the quantity 1 plus cosine omega t. So our normal acceleration now, that's going to just be a sub n equals the square root of absolute value of that acceleration vector squared minus a sub t squared. And our curvature of the trajectory, the curvature is where r equals the quantity a times the quantity 1 plus cosine theta. So that's going to equal, curvature is going to be that kappa equals 3 over the quantity 2a times the square root of 2 times the quantity 1 plus cosine theta. So that is part 1. Thank you very much and have a great day.